This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Before we get into the lecture today, a couple more of announcements to make, I guess. Just in terms of roadmap of where we are, we have 4 lectures to go, obviously, and this is one of 4. So you can grid them up nicely in a 2x2 matrix. This is today, so this is Q&A, or quantitative analysis. On Wednesday, we're going to do CS. It's really just one word, but look at cyber security with respect to embedded systems. It's a non-trivial thing, and it's something you'll see a hell of a lot of as you guys go off into jobs and industry. It's getting worse, basically, the situation. Then in week 12 on the Monday lecture, we'll do a bit of revision, but I want to talk about the assessment. I won't shorten that. Assessment. So revision and assessment, and then next Wednesday will all be about what's on the exam. Okay, when I say assessment, I'm going to talk about the report, and I'll give you some pointers about what to put in the report. I might show you some good examples of previous capstone reports, because the marking scheme for the report will be based on what a capstone report should look like. That should set you up for when you do the capstone project, right? You've done a report according to the marking scheme. So that's the next 4 lectures, the last 4 lectures to go. Now, I've had a whole bunch of people ask me about the Kabuki time constraint on getting around the obstacles and up and down the ramp. Now, I nominally set it at 60 seconds until I saw some people try and do it in 60 seconds, and I realised that I don't want the Kabuki to get broken, okay? So wheels lifting off and smashing into the obstacles because you're trying to nail it. So right, there's a couple of options. Who thinks that they can do it in 2 minutes? Their robot can do it in 2 minutes. Good, yeah, we've got one person. Yeah, okay, good. Who thinks 3? Who thinks 3 minutes? You can get it around the obstacle course in 3 minutes. No one, all right. So because I'm going to set it to be 3 minutes, okay? I'm going to up it from 60 seconds to 3 minutes now. I'll be generous, partially because I don't want you destroying the Kabuki by making them run at, super speed per hour and smashing into things. But also, I don't want you focusing on, having to try and tightly optimise stuff. I'd rather get reliability than optimisation in terms of speed. Okay? Now, there are ways of, if you're worried about a disconnect timer, when you disconnect the USB cable, there are ways around it by using either Wi-Fi, or there is a special command you can use on the command line which can essentially bypass any internal timers there are on the myRIO and the Kabuki. Okay, so this week in the workshops, the demonstrators will tell you if you've got problems with the 60-second timeout, they'll tell you how to get around that issue. Okay, so 3 minutes. I'll set that in the official specs and everything. I'll send out an announcement, but you guys are here on a 9 a.m. Monday, so you heard it first. Okay, it's 3 minutes. Right, what this does is it leads nicely into quantitative analysis. Okay? There's a whole bunch of references for this, mainly from chapter 16, but if you are interested in WCAT stuff, there's a good sort of survey paper down the bottom if you like reading paperish, academic stuff. And there's a good programming perspective for WCAT in the middle there. So it's a nice range of references. Okay. So we're going to look at representing programs in a graphical way, or as directed graphs, basically. And it becomes, predicting the execution time of them becomes a graph traversability problem. All right, and then we can turn that into a linear programming optimization problem. But what I really want to show you is how hard it is to do. And once again, it's not a trivial thing to do, and it's not something you can do very quickly and easily. And then show you that, I guess, there's a lot of scope for research in the area if you really want to get into it. And I'm not talking about academic research necessarily, but R&D in companies and things like that. It's an active area. And the fact that it might be not necessarily about predicting execution times and getting better ways of doing that, but perhaps rethinking the architecture around predictability. Okay, that's an interesting flip on it, and I'll talk about that at the end. Okay, so I'm just going to shift across here because I have an animation to show. So I'm going to go to a non-writable system. So when we looked at reachability analysis or verification, we looked at testing either safety or liveliness properties. And I'm sure that, right, you get the idea, you traverse an FSM diagram or whatever, and you can end up at a particular reachable state, or you can prove that you never get in a particular state. But we're going to add additional constraints on here now to say, let's put some timing in there. So not only does it have to get to a particular state, but it has to get there within a designated time. And a classic example is on a brake-by-wire system. So there's no mechanical connection between the brake pedal and the master cylinder and the actuators on the actual brakes anymore. Can we actually activate these within a millisecond? Oh, millisecond? Yeah, that's a millisecond. So it's a safety critical issue. The other side of quantitative analysis for embedded systems looks at power. So the top one's time giving a safety critical issue, dimension to it, but also power. If we're miniaturizing things, we're making them portable, then we need some sort of quantitative measure of how much power something can consume, right? So can some new app that comes along that someone's hacked up and coded pretty poorly, does it just kill the battery life on your phone, for instance, or consumer device? Now, that's not, that might be the extreme end of things. What about something a little more subtle? What about, say, a biomedical device like this little thing here that could be implanted in the patient and might report back data on the patient? So, for instance, maybe heart rate data or something, but it's implanted in the person. There are security issues with that, right? If it's a wireless sensor, you don't necessarily want people randomly just being able to read your heart rate, right? That might be a bit bizarre. So you need to encrypt it, right? And if these are micro devices, like that thing there that's about the size of a coin, then we need to ask questions about, well, if we're going to encrypt things, say RSA encryption, how much energy is actually needed to implement the encryption part of things? Not just the sensory stuff, but actually do the number crunching for encryption. And so you're very energy limited. You may be able to harvest some of the energy back by motion or something like that if it's an embedded, in a person sensor. But you need really good ideas on what these values are. And this is not just about sort of doing a really basic drain test on something and plugging some multimeter or something into this thing here. It's about robustly proving it via analysis of code using the hardware environment, etc. So that's kind of down at the micro scale down here, thinking about having to reharvest the energy because you need to implement encryption. What about a real cyber-physical system like a manufacturing process? For those of you mechatronics people might enjoy these sorts of videos. 3 robot arms. We'll do that again so you can see the 3 robot arms, right? There are 3 robot arms that are lifting and holding and spot welding, I presume, this particular vehicle here. We need some really, really tight bounds on how long these things are going to take to do their thing, right? So firstly, their 3 arms are synchronised. They're synchronised via a local network. The timing on the local network has to be super tight, right? So it's not going to be some just old network switch you go and grab or buy for $50 and go and plug some LAN cables in between these 3 things here, right? Because it doesn't give you any real predictability and it's consumer grade stuff. It's not time-stamped and synchronised, okay? So if these things get out of sync, if you can't predict the execution time of performing a task, it's disastrous, right? You're spot welding the middle of the roof instead of where the particular things join. Okay, so we can all appreciate the concept of knowing the precise timing of things. But it's even worse. These are cyber-physical systems. These things are running code on a microcontroller, microprocessor somewhere, and interacting with the environment, with the physics that the real world constrains you to, right? You can't arbitrarily quickly move a robot arm. You move a robot arm quickly and you get resonances, right? If it's like a truss structure, you tend to get resonance, right? Vibrations in it doing that. So it's a very complex situation. Not only do we need good models of the coding side of things and being able to predict the execution times of things like that, but also the damn physical system as well, and we've got those constraints. Okay, so life is hard, basically. That's the summary of all of that. It's hard, but it's exciting because hopefully for you guys, you've lived in a very isolated world. If you've come up with the undergraduate program here anyway, you're not exposed to all these sorts of issues. You build stuff in perfect bubbles and everything is happy and all that sort of stuff. But it's a bad world out there. Okay, right, but it's fun. It's actually, there are some really interesting problems here. Okay, when we did scheduling, I wasn't here for scheduling, but when you did scheduling, you would have looked at worst case execution time, WCET. Now, when you were looking at rate monotonic scheduling or earliest deadline first or whatever, you were just given those as numbers perhaps. There's a number, okay, go and implement an RMS that does something. But we're going to look into detail about where this comes from today. Okay, you just took it as a given, but where it comes from is actually, we're going to go down a path. Now, worst case execution time is important for, once again, safety critical things because you need a bound on, how long the maximum time something could possibly take. So that's typically for safety stuff. So I'd say WCET is particularly important for safety. And the brake example would be one to think about, right? What's the absolute worst case situation where you slam on the brakes and the actual, the brake pedal, you touch the brake pedal and the actual actuators do something? What's the worst possible case? That's a good one. But sometimes we don't really care about that ultra worst case. We're more interested in a broad behaviour. So you want a distribution of execution times, and you kind of want the shape of the distribution to say there's the mean and there's the average, the mean and the standard deviation, etc. So this could be for something like streaming, right? Media, who cares about media, right? You can buffer stuff. It doesn't matter if it comes early or comes late or whatever. You can sort of just, handle it. And if people get pauses as the video is running, it's not going to kill anyone, right? Really, you might get annoyed, but it's not going to kill anyone. Okay, so streaming might give you you might want a distribution, okay, as opposed to a singular point. So how do we do this? Typically, you try and find what's called a threshold property. So find some test case, one particular case that can violate the deadline. Okay, and if you find that, then obviously you found something worse, right? So you keep looking for particular cases that violate deadlines, and you're expanding out the distribution, if you like. And I'll show a graph that will make much more sense about that. So what the current situation is that we use software in the loop to do simulation. Now, hardware in the loop, it's the exact opposite of hardware in the loop, where you go and prototype the hardware in the actual situation. Here we're doing the opposite. What we do is we take, e.g., Simulink, or if you really dare, a LabVIEW model of a continuous time system, so the dynamics of a continuous time system. And what we do is then we bolt it in with a software model of what we're doing, right? So it's all in software. There's nothing physical happening. We take continuous time models, shove them together, and we try and predict the execution times that way. Okay, so this obviously software in the loop is much easier to do than hardware in the loop because we're not physically going and using the hardware, but it depends on the accuracy of your models here, right? With how good Simulink or how good old LabVIEW is. Okay, it's very important though that everything here, time is mentioned everywhere here, everything is synchronized, right? We need exact measurements of time, particularly if we're going down to microsecond or nanosecond scales for things. Maybe not nanosecond, that might be a bit too quick for the physical side of things, but micro or millisecond time scales, we need accurate timing. And everything needs to be, that's timing, and everything needs to be synchronized. To show you how non-trivial it is, I've got a little example down the bottom, but we'll go over WCAT and BCAT. So WCAT, we can all understand that. So it's the worst time taken by a software task, one particular task to execute, and it's a function of the input data that you're getting. Okay, so you could think of, particular values. You your software make decisions based on those values. You may have to wait for the physical side of things to happen in order you can get the input data, right? You think if there's something in motion and it's only detecting one particular point, and then the pendulum slows down, right? Your WCAT's going to get worse, right? Because it's not sampling it as quickly. And this is a pendulum, right? It's a physical system. So you've got input data, but you've also got environment conditions. What do I mean by environment? I mean environment of the hardware, not necessarily environment, okay? So this is stuff like software. Is there an operating system running on your embedded system, or is it bare bones, nothing sitting there? Environment conditions. So how's your memory organised? Is it chock full of other crap in there? Or is it open slather? You can do anything. Is there Is there a network involved? Are there delays with getting sensor data? Well, that could go back to the input data bit there, but is there some sort of network involved as well where you have to wait for other things to happen? Okay, so the opposite of WCAT is BCAT. It's pretty obvious. You swap the W for a B and it's best case execution time. That's not necessarily as important. It's a bit dangerous saying that, but typically WCAT is more important than BCAT. Best case, you know. We're always worried about the worst case. So, for instance, a very simple piece of code, one line. I know it has pointers. I know you hate pointers, but it's a nice example. So we're just setting something equal to 10 by dereferencing a pointer x, right? If we say, let's find the worst case execution time for running that, let's pick a hardware, let's pick ARM Cortex-A9. It's a dual core processor, so there's some thing going to happen there. For a particular architecture with a particular memory map, we've got memory involved here. It's not easy, right? Particularly when we have a dual core processor. What if there's other things going on at the same time? Processor gets suspended maybe halfway through this, because this translates to assembly code would be probably a few lines of assembly code. It might be a couple of lines, retrieving something, storing it, then going dereferencing the pointer, and then the memory store. So that's not necessarily an atomic instruction. There might be 3 or 4 instructions associated that with in assembly code, and you're in the middle of one of those and an interrupt comes in, or a context switch or something weird, and off you go. So even something as simple as just doing a pointer, an assignment via a pointer, very difficult to predict. We may have to run a lot of test cases. We may need to know an awful lot about the architecture itself. So here's a nice graph showing you the problem that we face. Now, there's a lot going on here, but in black, so the dark curve there, imagine that's somehow the real situation. We will never know the real distribution, right? Just with any statistical thing, we can just take a lot of samples and hope, law of large numbers sort of thing, that it comes out what the real world is. So let's pretend the dark curve here is the real world. This is time, and this is, I can't see the axis here because my thing's in the way. So that there is the frequency of time of something, of that particular time happening. Okay, so let's run a particular task over and over and over and over again. We get a big distribution, okay? And the frequency is vertical and the horizontal is the time taken. So this here is, I say actual, we never know the underlying distribution. And the grey there is the amount of times you've run, say, the experiment, or you've done some sort of simulation or whatever. And eventually it will hopefully match the dark curve there. Now, here's something important to mention. So WCAT is with respect to the real world, the actual system, okay? And it is either found or it's upper bounded. So it's never going to be perfect. So if we only took a few samples or a finite amount of samples, right, the worst case we may get in the light grey here might be there, which underestimates the real worst case execution time because we simply haven't done enough testing in order to get the tail end of the distribution. Okay? And likewise, we can have a discrepancy here with the real BCAT and the observed BCAT. Okay? So, yeah, it's an interesting problem here, right? Do we just do sufficient experiments, get that grey curve, and then say, yeah, let's just bump a bit extra onto that, and then maybe that should cover the real WCAT time that we could foreseeably get. Okay, so we've got measured and we've got possible, and obviously the possible is a wider range possible is wider range than measured. Okay, here's the problem. So given some code, and let's stick with C code because that's fairly universal. Given a platform, so some sort of system that it's operating on, perhaps Linux or something like that, and the hardware, how do we find the worst case execution time? Why is it important? And why do we focus mainly on WCAT than BCAT? It's because of the two things, correctness and performance. So the correctness here is again partially due to safety. Okay, task has to finish, right? With those synchronized robot arms, one of the robot arms has to finish its movement perhaps before the other one does something. And you need to know, guaranteed, that it's not going to, its worst case of movement will be a particular time because then the other one has to start doing something, okay? And then performance, and this would be things like rate mean scheduling, etc., right? Once we get values of WCAT, then we can start thinking about scheduling tasks in a system. So, can WCAT always be found? Measured, yes. We can keep sampling some system and eventually maybe we'll get close to the WCAT. We can measure it, as in just take timing intervals, but can it be found in general? No. No. Think about what WCAT is. Go back to here. It's this. What if you have a program, a task, that never terminates? WCAT, well, where does it go? That way. It's infinite, right? So, in general, the problem's undecidable. You have to actually set up code that predictably terminates a task due to some condition. You can't have infinite loops and stuff like that because then obviously, well, then WCAT doesn't exist. And is knowing some magic value, 10 milliseconds of WCAT, even if it's close to the real thing, is it enough? No, it's not, because anomalies occur. So if a task finishes early or something like that, then it may destroy what we're trying to do here, right? We're trying to do performance and correctness. So a classic example could be where if you've got an operating system happening, you've got a task running and you're trying to measure WCAT on that, and maybe there's another context switch task going on, and then the OS decides to just kill one of them, right? Randomly. Maybe it's accessed a memory violation or something, just kills it. Then WCAT, you might be seriously underestimating what it really is because the OS decided to kill something. Difficult, very difficult. Okay, so most of the embedded systems you ever deal with can be summarised by 3 lines of C code in an infinite loop. That's it. That's every embedded program you'll ever see. We don't like loops terminating in the sense that if this is the top level program, right, we can't have, there's no notion of main.c just finishing, right? Because then what happens? I don't know. So there are 3 steps in an infinite loop. There's read some sensors, do some stuff with them, and then write the sensors out. Or sorry, write to the actuators to perform whatever you need to do. And this is your Kabuki program, really, when you boil it down to things. It's reading sensors, it's computing some stuff in order to make decisions about what to do next, and then telling the motors to turn, whatever. That's it. So the focus, so these are really, these are the physical interfaces, yeah? Right? Your sensors are a physical interface and your actuators, motors, they're physical part. The cyber bit is the compute part, and that's the bit that we're going to focus on with with WCAT. We're not constrained necessarily by physics here, right? We don't have to think about rotational stuff and moments of inertia and all that. We're just going to look at the predictability of the compute part in terms of execution time. Now, the code in here for an embedded system is particular to an embedded system, has loops with finite bounds. It makes no sense to have to try and measure WCAT if you've got infinite loops, right? It doesn't exist. You never terminate. No recursion. Computer scientists love recursion. Embedded systems people hate recursion, right? Recursion is where you call a function over and over and over again, and you can call it in a nested fashion like that. It's terrible for an embedded system because you can get stack overflows. You run out of memory space and things like that, okay? And it makes the predictability difficult. We also, for embedded systems, generally say that we're going to assume a single-threaded system so we don't have weird context switches and stuff going on that makes predictability hard, and that there are no interrupts that come, because interrupts are almost, they could be an arbitrary length of time, right, depending on what they are. You could be in the middle of the compute part, an interrupt comes in to read a sensor. Well, then we're messing with the physical side again. Okay, so let's treat it as three distinct bits. Read sensors, compute them, write to actuators. So here's a computational piece of code. What it does is not that important. It's part of a cryptography algorithm that, given a base B and given an exponent E, it does a computation on that via this little expansion thing here. Okay, if the exponent's even, it does one thing. If it's odd, it does another. That's all that's important. So the idea is, well, cryptography is important, right? If we're encrypting stuff, we need to have perhaps a reliable worst case time on how long this takes to execute, because if we're synchronizing things and sharing data or whatever cryptographically, then we need a tight idea of how long does this take to actually run in the worst case. What does the code do? I don't care once again too much about it, but we've got a while loop. We've got one decision that's made if the exponent ANDed with a 1 is equal to 1. So in other words, this is the odd part to take. Oops, that's odd. The odd part to take. And if that bit's not taken, then we right shift the exponent, that's the right shift operator, by 1, and then we do a different calculation. Every time, regardless of if we are even, odd or even, we take the 1 off this I index, which forms part of the while loop. It's initialized to a constant, which is nice, so it is therefore not dynamically allocated or anything like that, in the sense that it's not some user variable that just gets plonked in the middle of running. So this is actually at compile time. This is defined here. So it's all nice and tight, right? We know everything beforehand, before this executes. I'll come back to this in a minute, but the idea is, if we're going to be able to predict, right, we want to predict how long this thing takes in the worst case to execute as a task. So this is our task. We break it down into blocks. Just like when we had C code early on and we kind of looked at line numbers as states and you kind of trace through the code that way, you do the same in a control flow graph. Okay, or a flow chart, you can sort of call it that way. This is the piece of code before that's been shoved into this control flow graph. What happens is any actions can be combined in a block, then decisions can be combined in a decision diamond or a decision statement or whatever you want to call it. And in this case, with the if statements here, with the while loop here and the if statements, they're only binary decisions, okay? It's either 1 or 0, right? There's no in between. So, right, while I is greater than 0, doing this, otherwise we're not doing it. And the if statement, if this, otherwise, well, then it doesn't happen. So every block can be, every section of code can be drawn as a block, and then where there are decisions to be made or control flow statements, conditionals, they can be represented as alternative paths to be taken. And as again, because it's binary, we can say 0 or 1 either way. Sometimes these are represented as diamonds in flowcharts. That's a pretty poor diamond, but there's a diamond over the top. Decision diamonds like that, explicitly. Okay, so if we break this down into this sort of structure, we can then start tracing through the execution of the code. And what we're interested in is if we want to predict the worst case execution time of this code, we want to get the worst possible traversal through all this stuff here, taking any possible path that we can to get from block 1 through to block 6, because block 6 is the end of the task. It's the return out of the function. Okay, so we're interested in the longest path from block 1 to block 6. Now note, obviously, right, sometimes we're taking this path, and sometimes we're taking that, sometimes we're bypassing this, and sometimes we're going through that. So there is a range, dependent, it's obviously dependent on the things that are input into as part of the function here, as to which paths we're going to be taking. Now, this one's fairly simple because we have hard-coded constants in here, and we knew a bit about the algorithm that if it's doing this right shifting and it's checking even and odd, it gives a bit of predictability about how it alternates with the different paths it takes on each iteration of the loop. We also know that the loop will only run if that's being decremented. We're checking above 0. We know it'll be run, 32 times. Right? So at least we've got a bit of predictability there. The idea with this is then, what we do is we want to find the longest path through the program. We then get timing on each of these blocks, and then we come up with a sequence and can sort of roughly sort of add the times up, if you like, okay, depending on the sequence. So this is all about the program. Okay, so coming up with that flow graph is just about the program and working out the paths you can take through the code, like that. So we've got to find the longest path. We have to find the bounds on the loops to know how many times we're going to be iterating over those loops. And we may have to find dependencies amongst other different code fragments. So once again, if there are variables in the piece we're analysing that are set by other pieces of code, we might need to know what they are before we come and analyse this piece of code. Okay, then, once you've come up with a model like this, it then turns to the hardware side of things, processor behaviour. So for each of those blocks, those basic blocks, we're going to call them small fragments, we need runtime bounds on particular platforms. Obviously, setting some things like this will be very different if it's on different processors, different brands with different instruction sets, different architectures. Okay, so we have to then generate basically bounds for those little blocks. It gets more complicated again if there's cache involved, that good old cache again. If there's pipelining and pipeline stall, right, where you're fetching and decoding instructions and you get stalling. You do branch prediction, speculative branching. Wow, that just completely makes it much, much, much more difficult. And so what we do is we take the program control flow analysis and the hardware side of things and feed them into each other to get some model of the worst case execution time. You can see now how messy it's getting. Very messy. There are some examples in the text, and this is one of them that I'd like to show you, which is it looks all over the place, but it's a very simple algorithm. But to get wket for it is potentially, ugly if we try and make it in terms of a control flow graph. So what does all of this stuff do here? Typically, in big data structures, you're looking at matrices or tables of data, and all this does here is it just iterates over every row and every column. Can't remember what order it does it in. Who cares? It doesn't matter. But it goes over every element in a two-dimensional table, okay? And all it's going to do is if the value in that array or matrix is positive, then we keep a running total of the positive elements and we count the fact we've seen a positive one. And if it's negative, then we add to the negative total and we keep track of how many negative ones we've seen. A very standard algorithm, search along row by row or search along column by column, doesn't matter, and add stuff up, accumulate. Now, if we want to put that into this particular sort of flow graph here, how many paths can we get through the code? Let's make it a fairly small matrix, 100 by 100. That's tiny when we're dealing with large data sets these days. It could be ordered 10 to the 6 by 10 to the 6 or something, right? But let's just do 100 by 100. How many ways can we get through the code here? Well, clearly, if it's 100 by 100, we have to check 10 to the 4, right? So we have to check 10 to the 4. So 10,000 elements have to be checked. Okay, so we're looping, we're iterating 10,000 times, obviously. But what's happening inside here? So the loop's running 10,000 times, but in here we are doing what? We're doing a comparison, and then if that passes, we're doing one operation. If it fails, we do the other. So there are potentially two different paths to take. Imagine an all-positive matrix, right? We're taking this one every time. Imagine an all-positive matrix with one negative number. We take this, 9,999 times, and we take that one. It turns out the amount of paths through this program is actually pretty terrible. It's 2 to the 10 to the 4 because we have two operations possible in the middle. Wow. That's crazy. Do we have to analyse all those paths to see what the worst case performance is there? Maybe. What if there's context switches and all sorts of other stuff going on? Wow, it's just too hard. Okay? So we have to have some constraints on what our platform can do here. Right, so well, that's just how many times around the world? 10,000 times. Okay, so the common approaches to doing this, what we do is we try and get a processor behavioural model, okay? And that's manually constructed. So that is basically then saying, looking at data sheets, timing on all of that, and coming up with a dictionary, if you like, of operations and how long it takes them to happen for a particular processor. Remember, we're interested in wket for a bunch of tasks, not for atomic operations. You can go and look that up in a data sheet. That's easy. But we want a task, and not even in assembler, a task in C. So it's one step, 2 steps removed from what's actually happening on the processor. Okay? What's happening on the processor? You've got C, you've got assembler, then you've got machine code. It's 2 steps away, but we still want to be able to predict the timing on that. Now, this is what we do. So we get sort of a list of all the operations that could happen and their timing on that. Then what we have to do is pick a starting state of the processor, because remember the processor, this task could happen with the processor all mixed up, half of its cache full, register's half full, or it could happen all empty, and so we don't have to worry about cache misses and hits and all that sort of stuff. So what we do is then, for each block, we then measure execution times of the blocks from those starting states. Okay? So we've got to pick reasonable initial states, maybe knowing what else is happening on in the program for this task, and then work out how long it takes the execution time for those. So coming up with these starting states is also an interesting thing. It may involve assumptions about the particular setup of the system. Then these times become upper bounds for the time on each block, and then we formulate an integer linear program to find the maximum sum of these bounds along any program path. Whew. So we've come up with a graph that shows the flow of the program. We've found worst case execution times for each of those blocks, given an initial state and a model of the processor. And now we need to then find the worst case through all those traversals. The easiest way to do it is to show you by a very simple bit of code. So up the top there is just a very simple piece of code that runs a while loop. It initialises a couple of variables so they're known at compile time, and we just build up Q, okay, while Q is less than N, and then set Q equal to some other random crap at the end. So the graph, the control flow graph of this setup here is that what we do is each of these blocks represent some assignments, the while loop, an assignment, and an increment, okay, because they're separate operations. What we're going to do is, so these are blocks, block 1, 2, 3, 4, and each block we're going to keep track of how many times the block is actually executed by these X variables, because obviously how many times that executes will add to the total worst case. We're also going to count how many times the edges, okay, the interconnections between the blocks are executed as well. In other words, we'll know how many times a block is entered via each edge or exited via each edge. Okay, so for instance, obviously straight away we would know that D1 would be 1 in this case, right? It's only going to run this piece of, well, we're interested in this block of code, so it only comes through once from that perspective, and this would be 1, right? There's 1 in, 1 out. This is how the program, the problem is formulated. It's formulated as a linear integer programming problem. If for each of these blocks we have a measurement CI, and this is a measured upper bound, the time taken for those blocks to execute. Okay, knowing the processor model, and perhaps we can work those times out somehow, get an approximation of them. What we want is now timing behaviour about the whole task. So it becomes a maximisation problem, right? We want to find the worst case traversal through here. Which paths do you need to take to make it the worst case traversal? Now, once again, this is a trivial program, and it's very predictable anyway, because we know how many iterations it's going to have. This is just an example to show you how it would be done. Okay, so once again, if you're screaming out, I already know what the answer is to this program, this linear program, it's an example, all right? So if each of these takes CI to complete, the upper bound for each of these blocks, we need to maximise the sum of CI times XI, where the XI are the amount of times each block are executed. Okay, right? It's a linear program. It's just a weighting times the amount of times each block has run. And then we've got constraints, right? We've got the constraint that it only enters the top one once, so that total time is then C1, X1, when X1's 1, so it's just C1. And we can then work out Obviously, the amount of times you enter here has to equal the amount of times you leave. So D2 plus D4 has to equal D3 plus D5. It makes no sense for that not to happen, right? How can we have missing entry and exit points here? And same here, right? If we enter, we exit. There's only one possible in, one possible out path. So we'd end up with a whole bunch of constraints. And then we go and tell a computer to go and solve that. And it's a linear problem, a linear integer program problem. It's NP hard. The more constraints you have, right, the harder it gets to be able to solve all of that. But there's some good software which can use heuristics and stuff and can come out with a solution for it eventually, right? Grind through it. And that will give you the estimate on what WCAT would be for this particular task here. So it's not trivial, even though that code, that little piece of code there looks somewhat simple. That four-step process of getting the processor model, working out the timing for each of these blocks, and then solving an optimization problem is just for that little piece of code there to get a good bound on what WCAT is. All right. I'll quickly talk about this and then I'll talk about instrumentation and stuff next lecture, and we will merge into cybersecurity. But here is a little piece of code from a drone or UAV program. This is very, very typical embedded systems. This is a little PID controller to correct the altitude, basically. So you've got an estimator that tries to estimate the altitude. You've got a desired altitude. PID controller is going to get you to the desired altitude. This is the error between your estimator and where you should be. I think it was a closed-loop feedback system. Then your desired climb is just a proportional controller to do that, okay, to get you there. Now, because the error is a float in embedded systems, we're very, very worried about overflow and underflow of floats. Okay, so if you overflow a float, you can make the float too big. What happens? So what we typically do is we typically use what's called saturation. Okay, so variable saturation. So if the variable gets outside a particular bound, we saturate it at that bound, lower bound, or if it goes above something, we saturate it there. Okay, clearly we don't want stuff getting out of control. So for this little piece of code here, if we want to estimate, say, WCAT for this, how many possible paths are there through the code? Well, one path would be, well, it has to run this line always. So we've got one path would be run this, run that, run that. Another path would be run this, but it fails, then run that, run that. So it would appear that you have 3 feasible paths through this program. Okay, or yeah. Right, so you do that, or that, and that. But funnily enough, that actually assumes that climb max is a positive value. If climb max is negative, there's some weird stuff that will happen here with these things here, and you actually end up with 4 feasible paths. All these things can happen, right, through the code. Remember, when I say feasible path, think of each line of this code as some block. The if statements are decisions, and the assignments are action blocks. Okay? So even a simple piece of code like this has multiple feasible paths, and you might need to make assumptions about a variable or even a constant coming in to this piece of code here. All right. What that does is it adds additional constraints into your linear program, okay, that you may have additional amounts of times a block of code is run can only be equal to 1, right? Because if one or the other thing happens, the sum of them has to be equal to or less than 1. Okay, I'll leave it there. I want to give you a bit of a nightmare to say that if you have two tasks that have two parts to them, A and B, W cat T for the task is not the sum of both of them. Why? Because the environment can screw you up, okay, between adding these two things together. Okay, by environment, what do I mean here? I mean by caching, all sorts of other stuff going on here, right, can mean that the total task execution time is not the sum total of the individual